Okay, welcome. For those of you that haven't had me in class before, I see a lot of familiar faces. I hope you guys had a really good break, even the ones I didn't have last term. For those of you that don't know me, haven't met me before, I'm Dr. Johan, and this is General Chemistry 2, and that's also Chem 112. So if you're in the wrong place, you're welcome to get up and leave now. Otherwise, we'll keep going. Okay, so let's see. I just introduced myself, so maybe I will talk a little bit about me first. Those of you last semester heard most saw this. The only thing that has changed is that now instead of playing Pal World, I got a better computer, and that's more forgiving of Valheim, so I played way too much Valheim over break. I'm a chemist. My research is computational chemistry, so I collaborate with a group down at Virginia Tech, which gets me access to their big parallel computing center, which is really nice. They're also a fun group to work with. And so what I'm concerned with and what I work on is proteins binding to ligands. So it's related to drug discovery. So if you're trying to make a drug, you want to make a compound that will bind to a given protein target of interest very tightly. And so we try to do that with computer modeling, which works out well for me. I'm a big gym rat. If you're over at the gym much, you'll see me over there. I'm hoping to get there at least 3 times a week, maybe 4 times a week this semester. I also like to rock climb. I still rock climb, but one thing I want to let you know is that a little over a year and a half ago, I was rock climbing and I fell and I actually broke my back. So I have a back fusion now. I have chronic pain, and so I have good days and bad days in terms of pain. So if I make a face at you, the reason why I'm telling you this is if I make faces or something like that when I'm answering a question, it might be I'm just having a bad pain day. Okay, so I'm going to ask for a little bit of grace there. I really want to help you guys out. And I'm not looking to make faces at people, but sometimes I'm making just faces. Some of you, if depending on which epics you went to, you may know that I also like to do home brewing. So here's a number of things. They all look like they're apple ciders of some sort. In fact, this looks like, that was mine? I don't think those are mine. They look like some. I made apple ciders out of apples from my parents' like small orchard in their yard, and had all this crap at the bottom afterwards because they were apple chunks. But yeah, so I do that, and I also really like to cook. So here are a couple of my favorite recipes. There's a creamy corn pasta right here, and this is a black bean burger. So those are some things about me. So if you're interested in any of those sorts of things and you want to talk about them, I love to talk. So then why don't we switch from that and start talking about the syllabus? I want to go over the syllabus. I want to go over it. I want to make sure we hit the important points, but I also want to go over it as quickly as possible because going over the syllabus is boring for you and for me. Does anybody not have a copy? Okay. Website is not up yet. I am waiting for IT to take, I teach this section here and then I teach it again the next hour. I want to have one website for everybody so I don't have to do everything twice, so I'm waiting for them to get things up. Until we get those merged, I'll probably handle things by email. I'll send you guys emails of here's the things that are going on. Okay, so let's talk about first important thing in terms of this are when my office hours are. So my office hours, official office hours are 1:15 to 3:15 on Mondays, so today, and then 1:15 to 2:15 on Fridays, or by appointment. So if you can't make any of those times and you want to talk to me, I'm happy to talk to you during a different time. You can send me an email. You could use Navigate, which is what they want us to use on campus, although I haven't looked at it because nobody used it last semester. So I don't even know if I had to set it up at this point. I set it up last semester. Nobody used it. So feel free to either send me an email if you want to talk to me outside of those times, or just tell me after class. Okay? So I have availability beyond those times. So also, we're going to have quizzes on Fridays. So I found that was a great, Thursday nights is a great time to put help sessions. And so you'll see here that there's a help session, 7:30 to 8:30 p.m. That's on Google Meet. Looks like I didn't say it was Google Meet here, but I did give you the link. Okay? So we can do that on Google Meet. So this Thursday, we'll have a quiz this Friday. Okay, and so this Thursday night, if you want to come to that help session for some help before the quiz, I am happy to do that. Let's see. I have to put learning objectives in here. Okay, materials for the class. So you need to get Achieve for the class, and with Achieve comes this textbook. You're probably familiar with this because you did it last term, unless that you took Gen Chem 1 and then skipped a year, and now you're taking Gen Chem 2. If you're not sure about that, talk to me, but you need to get on the Achieve system. I will send you a link. I think I set up my class last night, but I want to verify that everything's okay with Dr. Anderson, and then I will send you that link by email today. You need the laboratory manual for the lab, okay? I don't teach lab, so you'll deal with your lab instructor for that. A laboratory notebook, whatever they want, and laboratory goggles. Same sort of stuff as last time. If you have questions on that, come ask me afterwards. I can either help you out or I'll be able to guide you to the right person. There's a statement here in academic integrity. I'm not interested in going through all of that. It is important. You don't want to copy from other people. You don't want to have a cell phone out on a test or anything like that. On exams, if you need, or quizzes, you need to leave the room. You need to bring your cell phone up and hand it to me, okay? In terms of another academic integrity related thing is that you need to be using a non-programmable calculator. So I didn't enforce this last time, and I don't have one to show you. And you guys may not have one either, but I'll show you one at some point that next time. But there were some problems, not in my class, but another class of people actually programming stuff into their TI-85s or whatever number they're up to at this point. So you need to get a non-programmable calculator. Okay, so it's a basic one that can do logs and things like that. But I'll show you some examples. Maybe I'll send you a link for when you can order one. In terms of AI, you're not allowed to use AI in this class outside of, in the homework, there's a built-in AI, and you're allowed to use that one, okay? So don't do it. Normal penalties for those sorts of things. This talks about bringing that calculator every day once we have one. Attendance, I'm not going to be taking attendance in this class, but we do important things in every lecture, all right? If you need to miss a lecture, you may have noticed, if you had my class last time, you know I'm recording, and I am still recording when I look over here. So right now I'm recording, and I will be posting these up to YouTube. I will send you a link for that, okay? Or we'll have a link up on the webpage. So I record our lectures. We have a lecture, I teach this class, and I teach the same class the next lecture. I'm going to post one of those, okay? Probably yours, unless something disastrous happens, like I have a really bad example, I'm like, oh gosh, I screwed up. Okay, in which case I'll correct it for the next class, and I'll post their lecture instead. Does that make sense? So you may not be the exact lecture, although for you guys it probably will be. Grading scheme is right here. Okay, with pluses and minuses on it. So we'll go with that grading scheme straight out. And then this is how things are divided below that up in terms of grades in the class. We've got the percentages of things for the class. In terms of grades in the class, those will be up on Inquire once the class has started. If past performance predicts future results, I won't have that organized with these percentages until midterm, and I have to, okay? So it may not, the total grade may not be reflective, but these are the percentages that will apply, okay? And then at midterm they will. In terms of Achieve, so your homework system, it's difficult for me to pull things from Achieve over to Inquire, and so I will probably at midterm pull your homework grades over, and then I will pull them over either right before the final, or I'll just pull them over after the final for a second update. So those grades will not update very often, and also your lab grades. Your lab instructors will send me your lab grades right before midterm, and then they'll send me right before the final, and I'll pull those in to Inquire in terms of how those are. If you have questions about your grades as we go along, or you're worried about something, or you want some sort of at least rough estimate, let me know, and I'm happy to do that, okay? But you can also always do it yourself using these percentages. Okay? I won't deviate from these unless we decide we have to for some reason, in which case we'll announce that in class. Let's see. So we have in-class work and homework. Mostly this will be homework for that category. So that homework is going to be on Achieve. So using that system, I encourage you to do all that. Probably most of you, since you're here, right? You did most of your homework or all of your homework. Take that seriously, okay? The way I do that homework is I'm going to give you unlimited retries. So everybody should be able to get 100% on the homework. Okay, so you'll be able, if you get a problem wrong, you'll be able to try it again. It probably will give you different numbers sometimes at least, but you can try those until you get them and get full credit on those. I do drop your 2 lowest in-class homework assignments or homework assignments. Okay. Quizzes. I'm going to give them on Fridays throughout the semester. The only place that we might have exceptions to that is, I think all our tests are on Wednesdays, so I don't see a reason not to give quizzes every Friday. If we had a quick test the next day or something, it's not as useful. But we'll do that, and I'm going to drop your lowest 2 quizzes. Okay? Exams, there were 3 exams. Okay? And then there's also a comprehensive final. The final will cover the whole class. It will be what's called, it'll be mostly an ACS exam, so American Chemical Society standardized exam. So unlike the finals you took last term, this is going to be a multiple choice final, okay? And there are study guides that you'll be able to buy for, if you want for that. It's not a money-making thing on our part. You're not required to buy them. And I guess I probably have a copy somewhere if somebody wanted to borrow it and look through it and see what the questions look like, okay? But I'll give you some examples when we get closer to the end of the class. Laboratory, the important thing about the lab is you have to pass the lab to pass the class, okay? Note that. Accessible education services, so if you have accommodations for the class, please let me know as soon as possible. If you have accommodations, I just encourage you to set those up and be ready to use them, okay? Sometimes people have them and think, oh, I'm not going to be in this semester. Chemistry is a tough subject, so I'd encourage you to just get those set up and be ready with those. If you need more help, please get it. We have tutoring in the help center over in the library, I think. Is that where it's in? Okay, it's in the library still. So over in the library, there's tutoring. We have, I think Hayes is still doing it. He's excellent. All the other tutors are probably excellent as well. I just know Hayes. But he's really good, and they're all really good and happy to help you with those sorts of things. So take advantage of that. Take advantage of my time. I really want you to do well in here, right? We all want you to do well in here. So please take advantage of as much help as possible and as soon as possible. As you probably got a feel last time, and as you'll get a feel when I start my introduction, chemistry builds, right? It's we learned this, then we learned this that we needed that for, now we learned this that we need that and that for, okay? It just builds throughout this class, and the next class builds on that, okay? It's a very linear sort of thing, and much more linear than kind of almost any other topic in college. Final caveat is I might need to make changes to the syllabus. If we decide we need to do that, I will announce those changes in class. I'm not looking to make a lot of them. Questions on the syllabus? Outside, I had a great question about, or comment about how, I don't know if it's twice in here. Actually, I don't have an initial schedule. So in the back schedule, apparently I have our exams at 8:30 p.m. It is not at 8:30 p.m. Those are 8 a.m. 8:30 a.m. to 11:30 a.m. And you notice there's 2 dates there. Those are both the dates for both of my Gen Chem sections. Okay? You're welcome to come to whichever one you like. I don't care. Any questions? All right, then let's start talking about chemistry. So what we're going to start off with this term is we're going to start off with intermolecular forces. And by the way, for those of you that haven't had me before, these notes will get posted, okay? So if you get behind, you're always welcome to say, hey, you know, if people to ask me to slow down and let them copy stuff, always welcome to do that as well. But these are getting posted if you get behind, if that's the way you want to do it. So intermolecular forces, and what intermolecular forces are they, it's what it says. Inter means between molecules. Okay, so they're forces between molecules. All right, and I was talking about things building. So if we want to figure out what the intermolecular forces between molecules are, we have to use a bunch of skills that we learned last semester. All right, so what we need to do is we need to know whether something's polar or not. Do you remember that? And to know if something's polar, first we have to draw a Lewis dot structure. And then we have to remember our shapes and how they're related. Remember, the Lewis dot structure tells us how many things are around a center atom. And once we know that, we can figure out what the shape is. And I didn't make a big deal of this. Maybe somebody else is, but VSEPR, there's an E in there, isn't it? Valence shell electron repulsion theory. There's not a P in it. PR. Valence shell electron pair repulsion. Something close to that. Okay. But we're going to determine the shape, and that's just using the way that you learned in whichever Gen Chem class you were in. And then once we know the shape, we can look at that and we can see whether we have polar bonds, right? We can determine polarity. Right, so we had to build these things. You had to know how to do Lewis dot structures to be able to determine the shape, and then you needed to be able to determine the shape to be able to see if it's polar or not. Right, polar, if you remember, was about polar bonds and about whether they're symmetric or not. All right, so that's important. And you guys have had like a couple months away now, right? So it might be that we've forgotten some of that. So why don't we do a little bit of review? Sorry, I'm trying to. Oops. Nope, it's this button. I will figure out all my buttons. I'm trying to use the full screen here. I need some room. There we go. All right, so let's say we've got, what's a good interesting molecule? Let's say we've got formaldehyde. All right, so formaldehyde. Oh, really? All right, so we got formaldehyde. Formaldehyde is CH2O. All right, we want to figure out, is it polar? Well, first thing we need to do is a Lewis dot structure. So what's the first thing we do when we're doing a Lewis dot structure? We're going to find the number of valence electrons. That's a great thing to do. Let's take, what's the second thing we're going to do once we've done that? While I'm standing over here. We're going to decide the least electronegative atom is going to be the middle one, right? Okay? And so we can look up here, and electronegativity is going to decrease as we go to the left and we go down. Okay? If we have a tie, just pick the leftmost one. All right, that's what we're going to do. And we can look up electronegativities in a table, but generally we'll use the periodic table. So let's start out and let's do those electrons first. So we've got the number of valence electrons, right? And we've got the atom. So carbon, how many valence electrons? 4, right? We count from the left. 1, 2, 3, 4. Hydrogen, how many valence electrons? Hydrogen is going to have, I think hydrogen is going to have one, right? Well, so we have one here. For carbon, we had four. 1, 2, 3, 4. And I have two of those hydrogens, right? So one each, so 2 valence electrons total there. Now, how about oxygen? Oxygen's the one that has 6, right? So oxygen is going to have 6. So our total here is going to be 12 electrons, is how many we have to play with. So then our center atom is going to be carbon because it's farthest over to the left, it's most electronegative, right? So we put that in the middle, and then we're going to go ahead and connect it to the other atoms, these single bonds. Your process might be slightly different than this, but what I really encourage you to do is have a process. Okay, don't throw electrons and bonds in and hope until it looks like it's about right. There is a process to do this that will always get you the right answer. I'm doing a process right now. If you're taught a slightly different process, that's fine. I wouldn't worry about it. Now what I'm going to do is well, what do I do next, actually? You tell me. Put 8 electrons around everything, right? Except hydrogen, which gets 2, right? Because we only need 2 electrons to fill up hydrogen over there, or fill up the row that hydrogen's in. So I'm going to go ahead, I'm going to put 1, 2, 3, 4, 5, 6 to have 8 around the oxygen. And then I'm going to go, let's count up how many we've used. Well, I can put them here, right? And let's count up how many I used. 2, 4, we'll do this. 2, 4, 6, 8, 10, 12, 14. I only have 12, it's too many. If I use too many electrons, how do I fix that? I make a double bond. So let's go ahead and erase the one on the center atom, take them from the center atom, and then what I'm going to do is I'm going to take these electrons and I'm going to move them down there to make a double bond. And so now it's going to look like this. All right, and that's a good Lewis dot structure, right? I'm not going to spend time right now on formal charges, but a good Lewis dot structure also has formal charges where everything is equal to 0. All right. So if you have questions on home, and that's the case here, right? We'll do 1 atom per formal charges. So you may not always be able to do that, but for formal charges, the way I like, we had a formula for this, right? The formal charge was equal to the number of valence electrons, which would be, well, let's do oxygen right here. All right, so oxygen, 6 valence electrons minus the number of pairs electrons it doesn't share, right? Minus the number of bonds, okay? Unshared, sorry about my writing here, this is why I type whenever I can. Unshared electrons, and then this is, we have 2 bonds to the oxygen, number of bonds, and that equals 0. So that's how I know my formal charge is 0 for oxygen. All right, carbon has 4 valence electrons, and it has no unshared electrons. It has minus 1, 2, 3, 4 bonds. It's also 0. Okay. You'll probably get used to seeing what these things look like. Okay, when oxygen has 2 bonds, its formal charge is 0. When carbon has 4 bonds, its formal charge is 0. Hydrogen, 1 bond, formal charge 0. You get used to that. Fluorine, 1 bond, formal charge is 0. All right, so try to get used to that sort of thing. All right, what's the shape of this going to be, right? So what we're working through here is we did our Lewis dot structure. Now we need to determine the shape. Remember, the shape is determined by, I have a center atom, and then I have 1, 2, 3 things around it. How can I spread those 3 things as far away from each other as possible? what shape spreads them as far away from each other as possible? Trigonal plane, or a triangle, right? If I put them in a triangle and a plane, they're all 120 degrees, right, from each other would be our angles there. And so what we get is if we think about just what the shape is here, right? Now we're not doing a Lewis dot structure anymore. It looks like that, right? Trigonal planar. And if I don't like that because it looks funny, I can just do this. But trigonal planar is our shape. Now we need to figure out whether it's polar or not. So for a molecule to be polar, what's the first thing we look for? It must have polar bonds. Okay? Right? Remember, polar bonds are based on differences in electronegativity. And then the second thing is that the polar bonds can't cancel. The shape must be such that the direction of the polar bonds doesn't cancel. Now, I don't have an electronegativity table here, but it just so happens I've accidentally memorized electronegativities of all these atoms, so I don't need to do that. But you could look up the electronegativities of these atoms. But let's actually, before I do that, which of these is the most electronegative? Oxygen. It's farthest to the right on the periodic table and farthest up, right? Okay. And so I actually know these electronegativities. So the electronegativity of oxygen is equal to 3.5. All right. And the electronegativity of carbon is 2.5. Okay. And the electronegativity of hydrogen is 2.1. All right. So if I want to think about whether these are polar bonds or not, I can go ahead and I can figure out the electronegativity of that bond. I guess I could do C del bond O for the bond there. That's going to be equal to, I just need to look at the absolute value here. So I'm going to just take the bigger one. I'm going to subtract the smaller one, right? 3.5 for oxygen, 2.5 for carbon. That gives me 1. Okay. What was our line for a polar bond? At what point do we call something polar? For the electronegativity difference, right? Remember what's going on here. Well, I want you to try and picture the atoms as much as possible in this class, okay? This is more electronegative, which means it's pulling these electrons towards it. You're going to give me what the line was? It is 0.5 or more, okay? So this is 1. That's more than 0.5. Okay, so more than 0.5, so polar, right? That's a polar bond. So we have a polar bond, great. Okay, let's see what's going on with the other bonds and whether we have to worry about them much. So the other bonds are, we have an electronegativity of a carbon-hydrogen bond. That's going to be 2.5 minus 2.1 equals 0.4. That's not polar, okay? Not polar. So what I can do here is I can draw an arrow we like to draw these arrows like this, showing where the electrons are being pulled to. They're being pulled towards the oxygen, and the positive side is over here, which is why I do this little cross thing, but that's the way it's going, okay? We have no other polar bonds here, so nothing to cancel this out with. So is it polar? Thank you, sorry about that. Is it a polar bond? It's a polar molecule, okay? The molecule is polar. Questions on that process? Lots of stuff in there, right? We had used something in this class. I try to isolate concepts if I can, so that if you don't know how to do one concept, you don't get hung up on the next concept, but it's not always possible. This is definitely one of those cases where we have one thing, Lewis dot structures, and then we have shape, and then we have polarity. It's a lot of things to hold together. Okay, so if you're having trouble with this, please practice it. All right, so the molecule is polar. All right, and so what we would say is it has a dipole, okay? It's polar, it has a dipole. It has a permanent, sorry, dipole, okay? All right, and so what you could imagine, don't look too much at this figure yet, although we're going to get to it. So let me push it out of the way. That these guys could line up then, right? You have these in solution, they could be attracted to each other. It's we'd have a intermolecular force here where we'd have a partial negative charge. That little squirrely thing is a partial symbol. It's from calculus. We're not going to do calculus in the class, but we might use some of their terminology. And it'd have a partial positive charge here on this end. And so in solution, you might imagine these guys would line up. Like this. So I have this I've got a positive charge over here and a negative charge over here. It's partial, not a full one. And that this negative would be attracted to that positive. So these might line up like that. That would help hold them together in solution, right? Okay. And the way this manifests itself is it manifests itself in terms of, well, melting point, but also we're going to focus on boiling point. Okay. So traction, actually, let me write it. Let me type it. Traction between molecules manifests itself or can be observed, let's say, through boiling points. All right, so let's really quick, just to think about that before we look at some more examples. If I have, let's remember what our solids, our definitions for our solids, liquids, and gases. So solids, what's going on with the molecules? I've got your hands could be your molecules. You can hold them up. Yep, like this, okay? The molecules are close together and they're not moving. Okay, that's solids. Liquids. How are liquids different? Yeah, so molecules are close together Right, so we can get a variable volume because they can move around and fit the container they're in. We're just going to stay at the microscopic level here, but they're close together and they move relative to one another. I could say they can move relative to one another, but they just do if it's a liquid, right? They are moving relative to one another. And then gases. Molecules, how are molecules different here? They're very far apart, very, very far apart. And they move relative to one another. So if we think about boiling point, or think about boiling, boiling is going from here to here, right? Boiling is going from a liquid to a gas. So the molecules are close to one another, and you have to pull them apart to separate them with a huge distance, which means you have to break these attractions. All right? So the stronger these attractions, the harder it is to pull these things apart. Does that make sense? The higher the boiling point. So let me go ahead and write that. The stronger the attractions, the harder it is to pull molecules apart. I'm saying molecules, but it could be atoms, right, or ions. The higher the boiling point. Does that make sense? You have to heat them up more, give them more energy to get them to fly apart. Okay, so that means the stronger that dipole, the bigger that dipole, the higher we'd expect the boiling point to be, right? We just talked about things being polar. Let me go ahead and make this big. So we've got this picture from your book where they look at a couple molecules that have different dipoles. Unfortunately, this is really small. But so we've got carbon dioxide, where we do have polar bonds, but they oppose each other in their polarities, so we have no dipole overall. The dipole is 0, okay? Here we have sulfur dioxide, where we do actually have polar bonds, right? They mostly oppose each other in this direction, but because it's bent, we have a little bit where they add up in that direction. Does that make sense? Right? We've got two polar bonds that are pointing in this direction. So we have a little bit of a dipole here, and then here we have acetonitrile where we've got a big dipole where it's all going in one direction. Okay? And the dipole is a sum of how much it's all going in one direction and how polar those bonds are, right? That's not reflected here, and we're not going to worry about calculating these dipoles. Now, you might be given one. But so 0 to small to large, and what you see is the boiling point, carbon dioxide boils at negative 79 degrees Celsius, right? Okay, and actually it's got a little asterisk here because you guys know what dry ice is? Seen dry ice? It's frozen carbon dioxide. It actually doesn't even go through the liquid phase. It just goes straight from solid to gas. But negative 79 degrees for that. Sulfur dioxide, negative 10 degrees Celsius. And then that's a stronger dipole, that's a lot of degrees difference. And then about the same amount of degrees difference to go to acetonitrile, which has this very strong dipole. You see how we've got that? So how strong the dipole is? Okay. So the strength of the dipole matters, but it doesn't always matter exactly. So now what I think I'm going to do is I'm going to talk about the 3 intermolecular reactions. I'm going to name them, having talked about kind of the basis behind them that we're going to worry about. So intermolecular reactions, interactions. All right, and so what we're going to do is we're going to have I'm going to rank them here in the right order. I haven't told you what a hydrogen bond is. Okay, I'll go ahead and define it right now. It's a special strong, and I'll talk about why, special strong dipole-dipole interaction. We'll define it in a minute. Then we also have dipole-dipole interactions. Okay, and this is the attraction between two permanent dipoles. All right, and that's what we drew up above. This, I'll be right back down for those of you that are still writing. These are two permanent dipoles. Okay, this is a dipole-dipole interaction. And then finally, we're going to have what we call London dispersion forces. Okay, your book talks about it. Sometimes they're called London forces. Sometimes they're called dispersion forces. Full name is not London dispersion forces. I learned van der Waals forces. When I talk to physicists, they say van der Waals. So it can be confusing, but I won't say van der Waals in here. So London dispersion forces, but I may say London forces or I may say dispersion forces. Probably say London forces if I decide to go shorter. But London dispersion forces, after that aside, are the attraction between temporary induced dipoles. Or I'm going to say, I'll say temporary too. The attraction between, I'm going to say small temporary, I think I'm going to put next to small, I'm going to put induced, because that's what we want to think about. I'll talk about what that is in a minute. Induced doesn't mean small, but in this case it does. Dipoles. So I keep saying dipoles, right? I've switched to this term dipoles, which I've internalized, right? I've talked about it for like decades on decades. But what's a dipole? We just talked about it. What is a dipole? It's okay to say something and be a little off. Go ahead. It's polar, right? So what do we mean when we say polar, though? What do we got? What's going on in the We've got positive and negative, which you may have been saying too. But we've got charges, right? They may not be full charges, we have partial charges. Okay? I talked to my biochemistry class. We haven't gotten enough into this. Chemistry is almost all about charges. It's either about small partial charges or big full charges, but it's all about charges. And all this attraction is all about charges. We have a bigger charge, we have a bigger partial charge, and a less big partial charge, and an even less big partial charge. That isn't always there. Okay? It's all about charges. Positives and negatives attracting or repulsing each other. You can explain 90% of chemistry using this. So these get stronger. And they get greater partial charge. And they get stronger because the partial charge is getting greater. Okay? Big concept in chemistry that we can apply to all sorts of things. And we should apply to all sorts of things. When I do my computational work, part of what the computer is doing, it does a bunch of stuff in terms of modeling, but part of what it's doing is where are the charges? Calculate the charges. How much are these attracted to each other? That's what the computer is doing inside for that work. And I can adjust how much I want those charges to count. Questions? Super big concept. Okay, so we have pretty well defined what a dipole-dipole interaction is, right? Let's talk about these hydrogen bonds. Okay, so we end up with a problem here where you expect that as the dipole gets bigger, right, you'd end up with more attraction force, and you do, but then there are these cases where that isn't quite true, right? We have an exception, and that's where we have to bring in the hydrogen bonds. So here's an example from your book where we see this exception. So we have methane, right? Why is methane not polar? It's showing the shape. Do I need to know the shape? I asked it like you didn't need to know, right? I don't. Why don't I need to know the shape?
All the terminal atoms.
What was it?
The terminal atoms are all the same as all hydrogen.
They're all the same, okay? So in part, that would relate to the shape, right? This is that tetrahedral is a shape that actually would have your charges neutralized by polar bonds. But I don't have polar bonds, right? The electronegativity difference from our previous example where we looked at carbon and hydrogen was 0.4, not polar. So I don't have polar bonds, I don't have a polar molecule, right? So if you're trying to solve one of these things and you don't have polar bonds, you don't even need to worry about the shape. But no polar bonds, okay? So it has no dipole, they go to 0, okay? Hydrogen cyanide, okay? Polar bond in this direction. I was gonna have you guys do it, but I wanna make sure I get everything done today. All right, so if we look at this, we've got a polar bond, oops, and we've got a dipole essentially that's gonna go this way, okay? And then water, we've got a dipole that goes this way and this way, right? We got two polar bonds that go that way and that way. So our dipole, if we add those together, would look like this. If we look at the calculated dipole strength, this one's about 3 and this one's about 2, and yet the boiling point of hydrogen cyanide, which is, don't mess with it, right? This is cyanide when you hear about cyanide. Is 26 degrees Celsius, okay? And the boiling point of water is 100 degrees Celsius, much, much higher. All right, so it's not going with dipole strength here. So what's going on? Well, the way your book likes to explain this, we'll come to this in a second, is that this is a special case. Hydrogen bonds are a special case of dipole-dipole interactions that happen when you have a hydrogen, I'm going to write this, you have a hydrogen attached to an oxygen, nitrogen, or fluorine, bonding with or interacting with a lone pair on an oxygen, nitrogen, or fluorine. Okay? So, yeah, saw some people looking at the periodic table. Great thing to do. Always look at the periodic table, right? So much stuff on here. Nitrogen, oxygen, and fluorine are very electronegative compared to hydrogen. So let's write this thing out. Hydrogen bonds are special strong dipole-dipole interactions that occur when a hydrogen attached or bonded to, not attached, bonded to a nitrogen, oxygen, or fluorine interacts with a lone pair on a different nitrogen, oxygen, or fluorine. Okay, and I'm going to give you some examples really quick here. So we're going to do a lot with water because water it's the solvent of life. It's super important. Okay, all sorts of things, examples in our real life we can explain using water. We'll do a lot with that, but I'm going to show you some examples that aren't water real quick. So if I have ammonia, I'm going to draw these little wedges. Ammonia has a structure that looks like this, okay? And ammonia can interact with itself. Imagine another one over here. Okay, and this right here, should have left myself some more room, is a hydrogen bond. It is the interaction between a hydrogen that's attached to a nitrogen with, a lone pair that's on a nitrogen. Okay, hydrogen bond. So you have to have these three other atoms involved here. This right here could react or could interact with a fluorine in hydrofluoric acid. So let's say I had hydrofluoric acid, which you want to run from, by the way. Very dangerous. This dissolves glass, goes right through your skin, dissolves bone. Chemists who work with hydrofluoric acid have to have an antidote right there. So if they spill some on them, they can splash this stuff on them right away. But this would also be a hydrogen bond, different atoms, right? Doesn't have to be the same atom. Although when we talk about water, we're going to be talking about the same molecules interacting. But here we have another hydrogen bond where we have a hydrogen attached to a nitrogen interacting with a lone pair on a fluorine. Does that make sense? What a hydrogen bond is? And so we can do a bunch of other examples as well. And then down here, we can see this is water. Let me put that up just a little bit in case people are still drawing. But here we have an example with water. Okay, this is why water has such a high boiling point, because we make these hydrogen bonds. So here we have, I don't like that one. They should be pointing more towards them, but we'll just accept it for now. It's the best ones are when they're pointing straight at the lone pair as opposed to this thing. But here we've got that there. You see how we got the lone pair to a hydrogen on an oxygen? Bonded to an oxygen. Okay, so that's the strongest force we're talking about, at least in this chapter. We're not talking about full charges. Okay, hydrogen bonding. All right, now 7 minutes to talk about. I'll talk about surface tension. Water also, because water is so attracted to itself, we get what's called surface tension, meaning it like beads up. Water is so attracted to itself that it's hard to break the surface. So you can do things like you can set things on top of water. Here's an example of a water bug taking advantage of that, right? It didn't just break through and sink into it's taking care, the water's attracted to itself so the bug doesn't penetrate through. It's attracted to itself so it makes these balls instead of spreading straight out, okay? It beads up right here on this leaf. And then the same sort of thing like you might see on your car, the water beating up as opposed to making a sheet, okay? It's attracted to itself. So it does that. You also see that with capillary action. So you've got a straw and you stick it in something. A straw is pretty big, so you don't get a lot of it, but you'll see liquid will go up a little bit in the straw. The thinner the straw, the more it will go up. So that's because water is very attracted to itself. All right, let's quick go over London forces. So London forces are, remember London dispersion forces are induced dipole-dipole interactions. All right, I'm going to put the word temporary in here. What does that mean? Well, all atoms have electrons, all right? And all molecules do. I'm going to go ahead and I'm going to start just talking about argon rather than a molecule. So let's say I've got an argon atom. Argon has a bunch of electrons. And I have another argon atom here. How many electrons in the outer shell for argon? Very good, 8. Okay, we've got 8 electrons there. So I'm going to give you a very exaggerated example. So we can think about those electrons flying around. Actually, they're clouds, right? Remember we had those shapes for things? The electrons are in a cloud. They can kind of be everywhere. But I'm going to draw them as distinct electrons for our example. Imagine, so sometimes they're here, sometimes they're there, but imagine at one instant, 1 nanosecond, for this is a super exaggerated example that would never happen. At 1 nanosecond, I have 5 of my electrons over here and 3 of them over there. What does that mean about the charge on this argon? It means that I have a partial negative charge over here, right? And a partial positive charge over here. What does this negative charge do to the electrons in this argon? What happens when I get negatives next to negatives? They repel, right? So this negative charge here is going to push these electrons over on the other argon. Remember, this is super exaggerated. It's much less than what I'm showing is it's like full 2 charges, right? And so it's going to it's going to cause these electrons over here to push over and would end up with a partial positive here and a partial negative here, and these can attract each other. This is very weak because it's not this full charge stuff we're talking about. It's super tiny differences in charge. In one instant, one atom next to the other pushes the electrons a little bit, tiny bit. So you end up with a tiny difference in charge from one side to the other, and they attract together. Okay? And this is why you can make things like liquid oxygen. Okay, you have to make it really cold, but it does stick together if you make it cold enough, because you can get these tiny little charges that'll attract each other. Does that make sense what's going on there? Okay, you can get this same thing going on with molecules. Anything with electrons does this. So if you imagine, let's say we have an ethane molecule. Ethane looks like this. Ethene looks like this. And it's got electrons in it, right? We've talked about different models, and we're going to use our Lewis dot structure molecules like this, but these electrons are kind of all everywhere flowing around. We're using a simpler model, and they can get pushed around as well. And so you could imagine in one instant, you'd have a very small charge on one side of this ethene molecule. I need you to stick with me all the way through here because it's an important concept, okay? But you could imagine that if I have some sort of, my electron cloud here, I'd end up with a very tiny negative charge over here. And that would induce in the electron cloud next to it a very tiny positive charge over here. Does that make sense? And the more electrons, these can all add up. So the more electrons, I'm going to say the stronger the force. But what I really mean is there's just so many places this can happen, okay? The tiny charges add up. Okay, I need you to stick with me for 1 second here while I draw one more thing for this, and then we'll be done. Remember that this is our weakest force, but it can be really, from up here, where was it? There. It's our weakest force, but it can become really strong if there are a ton of them. All right, so actually let's do this. up here, this protein, which that's a bunch of different ones. That's tons and tons of atoms, and it has a shape that it has because you have London forces in it, and there are thousands and thousands of them holding it together. Even though individual London force is weak, there are thousands of them in that protein holding that in that shape. That make sense? Okay. Thank you for your patience.